one of the nice things about these Zoom meetings is getting to talk to people on an entire continent at once, and to visit you more easily than I usually could. So what I want to talk to you today about is really some recent history over the past 7 years, really. Infinite dimensional Lie algebras and their enveloping algebras are something which very little was known about until 2013. So this is quite a new area in mathematics. So I'm going to start with laying out the setting, and then most of the talk is going to be talking about conjectures, because this is a new area, so there are more questions than there are answers. And please if you have questions, please stop and ask questions, and I'll do my best to respond to them. So let me start by giving an example of what is going to be, in some sense, the hero of this talk. So for me, the symbol del or partial is always going to mean differentiation by x. And the Witt algebra, which I always call W, is polynomials in x and x inverse times this del. So just as a reminder, polynomials in x and x inverse, what I mean here is Laurent polynomials in x with complex coefficients. So something like x plus 3 plus x inverse is an example. So W is, well, it's the algebra of derivations of the Laurent polynomial ring. In other words, if you look at all the functions from the Laurent polynomial ring to itself that obey the Leibniz rule, so d of fg is d of f times g plus f times d of g, then that's precisely equal to this Witt algebra W. They're all differentiation by x times some function. So that's fine, but it raises an obvious question, which is, in what sense is W an algebra, right? It's called the Witt algebra. I said it's the algebra of derivations, but usually when we say something is an algebra, we mean it's an associative algebra. That is, it's a vector space, which is also an associative ring. So we have two questions we need to answer. First of all, how can we combine two elements of W to get a third? If it's supposed to be an algebra, we'd better be able to do that. And then, is it going to be an associative algebra, or is it going to be some other kind of algebra? So how do we combine two elements of W? Well, let's think about the product rule from calculus. If I have two functions, two Laurent polynomials f and g, then of course the derivative of g times f is gf prime plus g primes times f. So let me write that as g del plus g prime applied to f. So this suggests that the rule for writing del times g, it's not equal to g times del, but it's equal to g times del plus g prime. And again, this comes directly out of the product rule, the first displayed line on the slide. There's a way to make this formal by talking about the differential operators on the Laurent polynomial ring, but I don't want to do that now. I just want to go with the equation that del times g is the same as g del plus g prime. Okay, so that's our basic equation. Del g is g del plus g prime. So of course that means that if I take f del times g del, well, I've got a del g in there, so I know how to resolve that to move the del to the right using this equation. So f del g del is going to be fg del squared plus fg prime times del. And that's not an element of this Witt algebra, because the Witt algebra is Laurent polynomials times del, and there are no del squareds in the Witt algebra. So this is not a way where we can combine two elements of the Witt algebra to get a third element of the Witt algebra. But when you look at this displayed equation, one of the things you notice is that there's an FG del squared, and of course, FG is the same as GF. The polynomial ring, the Laurent polynomial ring, is commutative. So what that means is that if I take F del G del and subtract off G del F del, then the del squared terms are going to cancel. And what I'll end up with is FG prime minus GF prime times del, which is an element of the Witt algebra. So this gives us our way to combine two elements of the Witt algebra to get a third. And we're going to define this as called a bracket. And the symbol we're going to use is square brackets F del G del. And it will be, by definition, this element FG prime minus GF prime times del. So we've answered one of our questions. We know how to combine two elements of W to get a third, but we should think about the properties of this bracket operation on W. So it's not associative. However, it does have some nice properties. It's linear in both factors. It's antisymmetric. The bracket of x and y is minus the bracket of y and x. And if you think about how to combine three elements in different ways with the bracket, then it's not associative, as I said, but it does obey this identity that the bracket of x with y bracket z plus the bracket of y with z bracket x plus the bracket of z with x bracket y, those all sum to 0. This is called the Jacobi identity. And these properties 1 through 3 are the definition of what's called a Lie algebra. So the algebra structure on W is it's a Lie algebra. So Lie algebras are ubiquitous. Some examples of Lie algebras: well, n by n matrices with entries from your favorite field, say the complex numbers, are a Lie algebra. And just defining the bracket of A and B to be the commutator AB minus BA satisfies these properties 1, 2, 3. And so you've got a Lie algebra. Now, if I take the commutator of any two square matrices, it's an exercise in linear algebra to see that that commutator has a 0 trace. And that tells you that what's called the special linear algebra, SLNC, the set of traceless n by n matrices, that's a Lie subalgebra of GLNC. That's another example. Easy example, maybe not very interesting. If I take any vector space V and just define the bracket of any two elements to always be 0, then you can check this satisfies these properties 1 through 3 trivially. And so that's an example of a Lie algebra. It's called an abelian Lie algebra because if the bracket did come from a commutator, and then AB would be equal to BA, and so bracket AB would always be 0. And then a whole class of examples. If you have a Lie group, G, so that is it's a group, but it's also a smooth manifold. So an example of this is the circle S1. Then the tangent space to the Lie group at the identity is automatically a Lie algebra, possibly over the reals. Let me not worry about what field I'm working with. And it's an amazing and beautiful fact that the Lie bracket on this tangent space echoes the structure of the group. And it echoes the structure of the group so closely that you can recover the group from the Lie algebra, at least in a neighborhood of the identity. So this gives you, in a way, two different ways to look at the same object. You can look at the group, which is probably curved, right? It's like the circle, it's a manifold. It may have a complicated structure, or you can look at the tangent space, which is flat, and sort of take the derivative, if you will, of the multiplication and study it there. And it might be easier to work in Lie algebra or in the Lie group, or maybe it's easier to work with the group. It's always useful to have two ways to look at the same object. Now, I'm a ring theorist, so I'm happy to have this non-associative gadget, this Lie algebra, but I'm much more, my natural home territory is in the associative world. So a nice thing to be able to do is to turn a Lie algebra into an associative ring. So let me give you the formal definition, and then let me do an example to show you what's going on. So the universal enveloping algebra of G, and I should say, by the way, that the convention is that Lie algebras are written in these lowercase German letters. So whenever I have a little g in this font, it's going to be a Lie algebra. And at some point in the talk, I'm sure I'm going to forget to say that little g is a Lie algebra, but it's always going to be a Lie algebra. So I've got a Lie algebra little g, then its universal enveloping algebra. Well, it's defined to be the tensor algebra on G modulo the relations that if I take two elements x and y in the Lie algebra, then their commutator xy minus yx defined to be the same thing as the Lie bracket of x and y. So what's this tensor algebra? Well, what I mean by tensor algebra is all possible non-commutative polynomials in the elements of the Lie algebra G. So let me give an example of this universal enveloping algebra construction. So I'm going to start with the Lie algebra SL2, SL2C, which is, I think in a lot of senses, the smallest interesting Lie algebra. So I want 2 by 2 complex matrices with no trace, with zero trace. So it's a three-dimensional vector space. A basis for it is these three elements, E, F, and H. And the enveloping algebra of SL2 then consists of all non-commutative polynomials in the variables E, F, and H, but it's subject to the rules that EF minus FE is H, HE minus EH is 2E, and HF minus FH is minus 2F. And of course, the terms on the right-hand side of these equations come from computing the Lie bracket in SL2. But I can think of this just as an algebra given by generators and relations, if I like, and forget that it came from 2 by 2 matrices. So I've now got this enveloping algebra, this universal enveloping algebra U of SL2. And one of the nice things about this enveloping algebra is that there's a nice basis for it. I can write any element of the enveloping algebra as a sum of monomials that look like e to the I, f to the j, h to the k. So what I do here is, a priori, I've got non-commutative polynomials in E, F, and H, right? So FE is not EF because those are non-commutative. So suppose I write down a polynomial that has an F times an E in it. Well, I've got this rule that says that, this left-hand rule here says that EF minus FE is H, or FE is EF minus H. So I can replace my FE by EF minus H, and that's in the correct order. You can use these rules to rewrite any element of U of SL2 as a sum of monomials where you first take E's, then you take F's, and then you take H's. And it's not hard to see that those monomials span the enveloping algebra. The fact that it's a basis for the enveloping algebra is a harder theorem, and it's called the Poincaré-Birkhoff-Witt theorem, or just the PBW theorem. And this works for any Lie algebra, for any enveloping algebra. So let's see what the PBW theorem tells us for the Witt algebra, W. So we first of all need a good basis for W. The obvious basis is to take a power of x times del. It works out well to let En be x to the n plus 1 times del. And so in the enveloping algebra U of W, we have the rule that En times Em minus Em times En is the Lie bracket of En, Em. And remember, that was defined to be Fg prime minus Gf prime times del. And when you work out what you get M minus N times E sub N plus M. So it's sort of, it's a pleasing relation. So I like the aesthetics of it. And the PBW theorem here tells you that monomials where you start with small variables and then go to big variables form a basis for the enveloping algebra U of W. So just to give a concrete example, I want, like, E1, E2 is in my basis, E2, E1 isn't, but I can use the relation to write E2, E1 as a linear combination of E1, E2, and E3, and so express it in terms of this basis.
Would I ask a quick question, please?
Yes.
Is this order fixed, or one can choose a different order and we can still have the same statement?
Yeah, no, I mean, it's not fixed. You choose an order, you choose a basis for your Lie algebra, you also choose an order on the basis. And then you get, and then the monomials where the variables come in that order form a basis. Okay. So since here my basis was indexed by the integer, obviously the integer is the obvious order is to say that 1 is less than 2 is less than 3, but I could have decided that I want to have to go 3, 2, 1 instead. And that would also give you a basis.
Okay, so it works for any order. Thank you.
So if the dimension of your Lie algebra is some natural number d, which is finite, then it's a general fact that the enveloping algebra U of G has all the good properties of polynomials in d variables, but it's more interesting. So some of the good properties, it's left and right Noetherian. So left and right ideals of the enveloping algebra are finitely generated. How big is it? Well, it has polynomial growth in the following sense. So I want to think for a second about how to measure the size of an algebra, of a non-commutative ring. So I'm going to take inside the enveloping algebra, I'm going to take a finite dimensional vector space V. I want it to contain the element 1. And then I look at the vector space V to the n. So that's all elements I get as taking n elements from V and multiplying them together. And I look at the dimension of it. And the dimension of it turns out to be proportional to n to the d. So from this Lie algebra of dimension d, I get a polynomial of degree d that measures the size of this vector space. So this is saying, in some sense, that d is measuring the size of the algebra, and in particular, the dimensions of this v to the n are given by a polynomial. So those are two properties which are similar to a polynomial ring in d variables that also has the growth n to the d in the same sense. Two-sided ideals, however, of this non-commutative ring are in general much harder to understand than two-sided ideals of a polynomial ring. So again, I want to go back to the enveloping algebra of SL2. That's my most interesting small Lie algebra. So that's three-dimensional. So prime ideals, let's look at prime ideals of polynomials in 3 variables. So this is what you study in algebraic geometry, and they correspond to algebraic subvarieties of complex affine 3-space. So what do those look like? Well, all of affine complex 3-space is a subvariety. algebraic surfaces are subvarieties. I could have curves, I could have points. Here's a picture of some of the subvarieties of real three-dimensional space, just to give you a sense of what the geometry of three space, the algebraic geometry of three space looks like. So now I want to compare what's happening with the enveloping algebra. So the enveloping algebra of SL2 has many fewer prime ideals. I've got 0, that's prime. For every complex number, I have an ideal which I've called I lambda. And then for the integers, for the non-integer lambdas, the I lambdas are maximal. But for the integer lambdas, the I lambdas are not maximal, and there are these bigger ideals, J sub n, containing them. So the picture of the ideals of U of SL2 looks like this, rather than like this geometric picture here. And in general, with finite enveloping algebras of finite dimensional Lie algebras, you have this very interesting interplay between continuous, these I lambdas, and discrete, these JNs. There's a mixture of continuous and discrete structure that makes them very interesting. So enveloping algebras of finite dimensional Lie algebras, well, they're fundamental examples of well-behaved non-commutative rings. In other words, if you have any property that a non-commutative ring might have, one of the questions you probably want to ask about that property is, does it hold for enveloping algebras? Or which enveloping algebras does it hold for? Because they're such fundamental examples, they're very well studied. And this interplay between the continuous and the discrete I was talking about gives them deep links with geometry, which I'm not, unfortunately, going to go into in this talk. So let me now move to talking about what I call big enveloping algebras, which is my shorthand for the enveloping algebra of an infinite dimensional Lie algebra. So in contrast to the finite dimensional case, they're very poorly understood, and most questions about them are open. So the fundamental question about big enveloping algebras is, take a good property of non-commutative rings. Does this ever hold for big enveloping algebras? So as an example of a good property, polynomial growth, but it turns out, this is a theorem of Martha Smith from the 70s, that the enveloping algebra has polynomial growth if and only if the Lie algebra is finite dimensional. So as an example, let's look at the Witt algebra, take a subspace of it, then the dimension of v to the n is proportional to e to the square root of n. So that grows faster than any polynomial. I'm going to have to ask you to excuse me for a second because my cat is making noise and I need to kick her out of the room, which is not a problem I usually have giving talks. She's gone. I apologize on her behalf. So we know that enveloping algebras, I asked if enveloping algebras are ever nice, and they never have polynomial growth. So what about Noetherianity? So this was actually asked in 1974. Is it possible for the enveloping algebra of an infinite dimensional Lie algebra to ever be Noetherian? So as an easy example, let's look at some examples of infinite dimensional Lie algebras. Well, any vector space can be an abelian Lie algebra. And it's pretty easy to see that the enveloping algebra is then just polynomials in however many variables is the dimension of your vector space. And so it's Noetherian if and only if you've got a finite dimensional vector space. Polynomials in infinitely many variables, ideals are not finitely generated there. So the next question to ask is probably about the Witt algebra. And Dean and Small asked this in 1990. Is this enveloping algebra Noetherian? It turned out this was an easy question to ask and a hard question to answer. And it sat there for 23 years until myself and Chelsea Walden answered it. No, this enveloping algebra is neither left nor right Noetherian. So I want to say a little bit about the proof, because it turns out that even though that question sat there for 23 years, in some sense, the answer was sitting in front of us the whole time. So I'm going to look at an associative ring, which I'm going to write. This is not standard notation, but I hope you'll bear with me, as polynomials in x, x inverse, and del. So del here is still d by dx. And here the product rule tells us that del times x is x del plus 1. So this is if I didn't have the x inverse, this would be a ring that is called the Weyl algebra. With the x inverse, it's, I guess, the localized Weyl algebra. Now, from the setup, W is contained in A, since W is Laurent polynomials times del. And in A, I'm certainly allowed to have del squared because it's an associative ring. And so this turns out there's a ring homomorphism from U of W to A, given by just sending f times del to f times del. I'm going to call that ring homomorphism phi. And I want to emphasize that this is the first thing you think about when you think about the ring theoretic properties of this enveloping algebra, is that there's this ring homomorphism to A. It turns out that the kernel of this homomorphism phi is the ideal that's not finitely generated as a left or right ideal. So the kernel of phi, in other words, gives us the answer to the question, proves this theorem that the enveloping algebra of W is not Noetherian. But interestingly, if I look at it as a two-sided ideal, then it's principal. It's generated by a single element as a two-sided ideal. So I want you to keep that contrast in mind. You need infinitely many generators as a one-sided ideal, but you just need one for a two-sided ideal. So as a corollary, we get that U of G isn't left or right Noetherian for a host of other examples of infinite dimensional Lie algebras. And I think I won't define any of the examples on this slide. The point is that there's no known example of an infinite dimensional Lie algebra with a left or right Noetherian enveloping algebra. For every infinite dimensional algebra where we've been able to answer the question, the answer turns out to be no, the enveloping algebra is not Noetherian. So let's move on to making some conjectures. Well, the obvious conjecture from the previous slide is that if you have a Lie algebra G, then its enveloping algebra is left and right Noetherian if and only if the Lie algebra is finite dimensional. Now, I believe that Dixmier made this conjecture a long time ago, back in the 60s, but I've never been able to find that in print. To my knowledge, the first time this conjecture appears in print is in my paper with Walton. So this is a conjecture that people have certainly thought about before 2013. I've thought about it since 2013, but it's hard. So I want to move on. This conjecture is too hard. I want to move on and make some conjectures that I might have more luck saying something about. So let's look specifically at the Witt algebra and make some conjectures about its enveloping algebra. So I want to go back to this homomorphism phi, which went, if you remember, from the enveloping algebra to this ring A. And I'm going to let B be the image of this homomorphism phi. So I want to tell you some things about B. So first of all, B satisfies the ascending chain condition on two-sided ideals. Here, what I mean by the ascending chain condition, or just ACC, is that if I have a chain of ideals, I1 contained in I2 and so forth, then eventually that chain stabilizes. That's the same thing as saying two-sided ideals are finitely generated. What you get from that is that U of W satisfies the ascending chain condition on two-sided ideals containing the kernel of phi. And since the kernel of phi is principal as a two-sided ideal, this says that two-sided ideals that contain the kernel of phi are finitely generated. Furthermore, this ring B has polynomial growth, whereas I said U of W does not. It's much bigger than polynomial growth. So from this example, this suggests, I claim, that ideals in the enveloping algebra, the Witt algebra, are both big and sparse. Let me say a bit more about what I mean by that. First of all, something that I'll call the growth conjecture. Both these conjectures were made in a paper of mine with Alexei Petukov in 2017. That any proper factor of the enveloping algebra of W has to have polynomial growth. Since the Lie algebra, since the enveloping algebra has sub-exponential growth, it grows faster than any polynomial, this is saying that ideals need to be very, very big, because when I factor out any ideal of the enveloping algebra, I get a ring that is much, much smaller than the enveloping algebra. So this conjecture was suggested by computer experiments that a master's student, Johan Stancier, did with me in 2016. A second conjecture: if ideals are big, then probably the structure of the lattice of ideals is sort of tractable. There probably aren't that many ideals. So let me call that Noetherianity conjecture, which is that U of W satisfies the ascending chain condition on two-sided ideals. We know it doesn't satisfy ACC on one-sided ideals, right? So I'm calling that ideals are sparse, because I think of it as saying, well, there aren't that many two-sided ideals. And what I want to do for most of the rest of this talk is to tell you what's currently known about these two conjectures. So first of all, the growth conjecture. The growth conjecture is now a theorem. This looks like it happened just after Alexei and I asked it, but it was actually about a year and a half later. So in 2018, Natalia Yudu and I proved the growth conjecture holds. So any proper factor of U of W does have polynomial growth. So the proof has some complicated combinatorics, but the main idea that we're using is a simpler commutative ring that's related to the enveloping algebra. So this is what's called the symmetric algebra on W, S of W. So what that is just the polynomial ring whose variables are this basis for W. So it's polynomials in infinitely many variables, E minus 1, E naught, E1, going up, going down. And this is not only a commutative ring, it also is something called a Poisson algebra. So what do I mean by that? Well, there's a surjective linear map, which I write GER, from U of W to S of W. And it's defined by, well, let me take GER and apply it to a monomial in the E's. And I'm just going to get back that same monomial, now thought of as an element of this commutative ring. And I'm going to define a bracket, which I'll use curly braces here, on S of W in the following way. Let me take two elements in S of W. I'll write them as GER of A and GER of B. Their bracket is going to be GER of their commutator, AB minus BA. This is a well-defined bracket. And for example, it gives you the rule that the bracket of EN and EM is M minus N, EN plus M. So just for elements of the Lie algebra, the curly braces bracket agrees with the flat braces bracket. So S of W is now a commutative ring that has this bracket on it. And that gives it the structure of something that's called a Poisson algebra. And it turns out that if I have a two-sided ideal of U of W, then Gur of I is not only an ideal of S of W, but it's a Poisson ideal. In other words, it's closed under bracketing with arbitrary elements of the Poisson algebra. So the idea of proving the growth theorem, that proper factors of U of W have polynomial growth, is let's make it easier by proving it for Poisson ideals of the symmetric algebra. So the idea here is if you think of an element of U of W as a non-commutative polynomial, then elements of S of W are sort of their leading terms through this growth, through this Gur map. And it turns out that the Poisson ideals of S of W capture just enough information about ideals of U of W, and they're easier to analyze because we're only looking at one term. So that's all I really want to say about the growth conjecture. I don't want to go into any more of the proof. Instead, I want to tell you something about what's known about the Noetherianity conjecture. So here, the statements that are proved are actually about what's called the positive Witt algebra, W+. So I'm looking here at the span of the ENs where n is at least 1. This is again a Lie algebra. It's symmetric algebra, has a Poisson structure, and it turns out that it has ACC not on Poisson ideals, we don't know that, but on radical Poisson ideals. Remember that an ideal is radical if you've got f to the n in I, then that tells you that f is in I. S of W plus, by the way, certainly does not have ACC on just ideals, full stop, without this Poisson structure. Because S of W plus, remember, is polynomials in infinitely many variables. In the variables E1, E2, E3, and on. So, for example, the ideal generated by E1 is strictly contained in the ideal generated by E1 and E2, etc. Or another way of saying that is that if I look at the ideal generated by all the variables, that you need infinitely many variables to generate that. That's certainly not finitely generated. So having ACC is definitely a Poisson property. So the basic way that we proved this was by showing that if I take a radical Poisson ideal of the symmetric algebra, I can embed it in a finitely generated commutative algebra, which then will have any good property you want. In particular, it will have ACC on ideals. This is by the Hilbert basis theorem, the first theorem that proves that any ring is Noetherian. So I think I'm going to skip the proof of this lemma that embeds S of W mod I in a finitely generated commutative algebra. It'll be on the slides if people want to read it. But let me say what we get from this theorem, this proposition that SW plus has ACC on radical Poisson ideals. This Gur map lets you go from an ideal of U of W plus to a Poisson ideal of the symmetric algebra. We know that S of W plus has its ACC on radical Poisson ideals. And what we get from that, it turns out, is that U of W plus has ACC on ideals I, such that Gur of I is a radical ideal, which of course is not the Noetherianity conjecture, right? The Noetherianity conjecture was that U of W plus has ACC on all ideals I, full stop. And unfortunately, we don't know for which ideals in U of W plus is Gur of I radical. So this corollary is not as much help with the Noetherianity conjecture as we would like it to be. So I'm going to end up by stating one more theorem and two more conjectures, which are related to the Noetherianity conjecture. So here I want to think a bit more about the structure of S of W plus. And S of W plus is called the symmetric algebra of W plus. And I'm going to define the nth symmetric power of W plus, which I'm writing Sn of W plus, to be the vector subspace spanned by monomials of degree n. So S1 of W plus is just W plus, right? It contains things like E1, E2, E7. S2 of W plus contains things like E1, E2, E4, E5, etc. Now, if I take an element of Sn of W plus, then I can make the Witt algebra act on it by defining EI applied to M to be the Poisson bracket of EI with M. When you work this out, this is still something that's in Sn of W plus. So this is giving you an action of W plus on SNW plus, which makes the nth symmetric power, it gives it the structure of a module over this enveloping algebra. Or if you like, it's a representation of the Lie algebra. It turns out to be true that the second symmetric power is an Noetherian representation of W plus. And what you get from that is that U of W plus has ACC on ideals, which are generated by quadratic expressions in the EIs. I should say that S1 of W plus, that is W plus itself, is definitely Noetherian. So here I want to look at Lie ideals of W plus, and they're basically given by the natural numbers, right? For example, let me consider the Lie ideal generated by E3. Well, I bracket E3 with E1, which is a multiple of E4 that needs to be in there. I bracket with E1 again, that's a multiple of E5. So the Lie ideal generated by E3 contains all the ENs for N3 and up. So that's definitely satisfying the ACC. And so S1 is Noetherian. So S2 is the first interesting case, and it turns out to be Noetherian. So this is my own theorem with Alexei Petukov. But I have to say, I do not love this proof. It's through lots of very explicit computer calculations. So it's not pretty at all. And it's very hard to see how it's going to generalize to higher symmetric powers. This is not sort of the right proof of this fact. So let me close by stating two final conjectures, both of which I believe, but neither of which I can prove. So the symmetric power conjecture, it's a two-part conjecture, really. First of all, the nth symmetric powers of W plus and of W are always Noetherian as representations of the appropriate Lie algebra or as modules over the appropriate enveloping algebra. I think possibly the more important part of this conjecture is as a nice proof of this, a proof that doesn't look anything like the proof of the theorem on the previous slide. The other conjecture I want to make is that if we knew the symmetric power conjecture to be true, then we could deduce the Noetherianity conjecture for W plus and for W. Again, I believe this, but I don't know how to do this. So I'm going to end here. Again, thank you very much for inviting me to speak.